Our last section of notes is going to deal with Gibbs free energy, and so Gibbs free energy is represented by a delta G, and it's related to that enthalpy that we've talked about. And so we've learned that enthalpy, we want to get atoms into a more stable configuration, so we want those like to form stable things, and so delta H is favored, seems more favorable when we have exothermic reactions, so we expect kind of all reactions to be exothermic, which we don't see. And in the previous note section, we talked about entropy, and entropy is a measure of disorder, and so things want to go to more disordered. We saw that the bedroom got more disordered, and this is what we kind of expect. And so we have these two things that tell us whether a reaction is going to be like favorable or not favorable, and this is talking about thermodynamically. So a Gibbs free energy is favorable when it's a negative number, and that doesn't mean the reaction is necessarily going to happen or happen fast or happen slow. It's just saying this is what it wants to do, and there's things like activation barriers and things that hinder things from happening, or we can modify the system and we can put in an electrical charge or something and force things that don't want to happen. It's kind of like you don't want to clean your room, but if your parents yell at you enough, it's still going to get cleaned. So that's what Gibbs free energy is. All thermodynamic favorable chemical reactions have a value for the Gibbs free energy, not the GO, that is negative. So if it's thermodynamically favorable, the Gibbs free energy is going to be negative, and if it's positive, then it's not going to be thermodynamically favorable. The math of the equation above, or I should say below, tells us that negative delta G is favorable by a negative delta H. So we just talked about this. We want a negative delta H, and then sort of subtracting, we'd want a positive S, because a negative times a positive gives you a negative. And so if we have a negative delta H and a positive delta S, we know for sure that this reaction is going to be thermodynamically favorable. Important things to know, and there's a note up here, is that when you go and you calculate these, delta H's tend to be in kilojoules per mole. Gibbs free energy tends to be in kilojoules per mole, and delta S's tend to be in joules per mole. And so if you are doing this, you need to make sure you end up in all the same units. So you normally have to do unit conversion on the delta S to make it kilojoules per mole. Not always, but normally. So just keep in mind, units are your friends. Just because the reaction's happening doesn't mean it's happening fast. So they may not be able to measure those rates. And then we haven't talked about equilibrium, but that's what this K is, and we would expect K to be greater than 1. If K is at 0, then your system is at equilibrium. And so we'll talk about that more when we get to equilibrium. We'll talk about it a little bit at the end of this section of notes, whether it's this video or the next one, I'm not sure. So as we saw in the page 4, delta G equals delta H minus T delta S. So this is like a common type of thing that kind of ask you on an AP test or on a test is what's causing the reaction to be thermodynamically favorable? Is it going to be thermodynamically favorable? If it is it going to be at high temperature, at low temperatures, or always? So if delta H is positive, that's not going to lead to a negative number, so that's not going to be the leading cause. But if delta S is positive, then this could be thermodynamically favorable. What's going to cause that is the delta S to be thermodynamically favorable. So if delta S is positive, then hey, we need a big number here so that it dominates, so we need a high temperature. So you get a negative delta G at high temperatures, but you'd end up with a positive delta G at low temperatures. And so at high temperatures, this reaction is more likely to be or is thermodynamically favorable, and at low temperatures, it's not. If we end up with a positive and a negative, then we get this negative times a negative, so it's always positive, and so this reaction is never going to be thermodynamically favorable. if we reverse the signs and we get a negative and a positive, then this is always going to give us a thermodynamically favorable system. And then lastly, if we have a negative and a negative, then this is going to be thermodynamically favorable at low temperatures, and then at high temperatures it's not going to be thermodynamically favorable because we're going to get that positive part for this second part, because we get a negative times a negative, which is a positive, and then when t is big, we get a big enough number to overcome the delta H. So if they give you delta H's and delta S's and a temperature, you can calculate the Gibbs free energy, tell if it's thermodynamically favorable or not. Or just like we saw with entropy and enthalpy, we can do the sum of the products minus the sum of the reactants. You don't see that a whole bunch, but you will see it. If delta G, if the Gibbs free energy is positive, then the reaction is not thermodynamically favorable. If it's 0, then the reaction's at equilibrium, and if it's less than 0, then it is thermodynamically favorable.